Avery, the applications astronaut, talking to you about differentials. I got another question. What's an astronaut's favorite dance move? That's going to be the moonwalk.
First thing you're going to do is review differentials. So we're going to let y equal f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted dx, is any non-zero real number. The differential of y, denoted dy, is equal to f prime of x dx. Now, where the heck did this come from? Well, we know that dy dx, or dy over dx, is equal to f prime of x. The derivative of your function is equal to the derivative of your function. Both of these things mean the same thing. So the key takeaway here is that dy and dx are actually two separate things. They're two separate entities. So what I can do is I can actually take this equation, multiply both sides by dx, and I end up with this equation for the differential of y. Now, what the heck do each of these things represent? Well, dx represents the change in x. F prime of x is going to be the derivative of f at a particular x value. And then dy, you think it's going to be the change in y, but it actually is just the change in y as the change in x, or delta x, approaches 0. So what does this mean? What am I talking about? Well, the major things you need to know here are dx and delta x mean the same thing, but dy is not necessarily the change in y, or delta y. It's actually approximately equal to delta y as delta x approaches 0. So let's quickly review the difference between the differential of y, dy, and the change in y, delta y. So when delta x, or the change in x, is a very small number, you may use the differential of y, dy, to approximate the change in y, or delta y. In other words, as delta x approaches 0, dy, the differential of y, is approximately equal to delta y, the change in y. So let's examine this. In this figure, we're going to see the difference between dy, the differential of y, and delta y, the change in y. So let's imagine we have this curved black function f. And at a particular x value, c, we know the y value of our function f is f of c. That's why there's a point at c, comma, f of c. We then look at another x value that's a certain distance away from c, and we'll call that distance delta x, or dx. Now, our new x value then would be at c plus delta x. And if we wanted to figure out the y value of the function f at that particular x value, we would just evaluate f of c plus delta x. That's why there's a point here at c plus delta x, comma, f of c plus delta x. That's the y value of this point. Now let's say, for instance, I wanted to find the difference between these two y values of each of these points. What I would do is just subtract the y values, and that would give me the change in y. That's where this equation comes from. The change in y, or delta y, is just equal to the two y values of each of those points subtracted from one another. But let's say, for instance, that this function is super crazy and it would be nearly impossible for me to figure out what this y value is and subtract it from this y value. What I'm going to do instead is create a tangent line to our function f at x is equal to c. That's where this blue line comes in. So in order to approximate the change in the y values here between this y value here and the y value for this point right here, to approximate this change in y, what we're going to do is figure out the change in y between this point on our tangent line and this point right here. So how do I figure out this value right here, the change in y for our tangent line? Well, that's where this formula comes in. dy is equal to f prime of c dx. What is that? This is point slope form for our tangent line. If you recall, point slope form is just the change in y is equal to the slope times the change in x. So this is just another form of point slope form. So there are two different change in y's that we're talking about. dy is just the change in y for our tangent line, whereas delta y is the change in y for our original function. But since that is sometimes hard to find, we can use dy, the differential of y, in order to approximate delta y as delta x approaches 0. And think about this. As delta x, this change in x, gets smaller and smaller and smaller, this point right here on our graph gets closer and closer and closer to our point of tangency, and this point on our tangent line gets closer and closer and closer to our point of tangency. And notice that the difference between these 2 points becomes almost negligible as delta x approaches 0. That's why we're allowed to use dy to approximate delta y as delta x approaches 0. Now let's talk about propagated error. So propagated error is a calculus-derived statistical calculation designed to combine uncertainties from multiple variables in order to provide an accurate measurement of uncertainty. Now what does this all mean? Well, let's say for example that you're using a physical measuring tool like a ruler or a tape measure, and you're measuring some object. When you measure that object with a ruler or a tape measure, you're going to get a measurement that we're going to call x. Now that measurement is not the exact precise measurement of that object because there's always going to be some error when you're physically measuring something. That error in your measurement we're going to call delta x, meaning that the exact measurement of that object would be x, whatever you got, plus the error in your measurement, delta x. So that's the exact measurement of your object, whereas x is just what you got. Now, what's going to happen is oftentimes when you measure an object, you're going to use that measurement to calculate something else, like the surface area or the volume of something. When you do that, your new value is going to be that f of x. That's what you get when you use your measured value to calculate something else, f of x. Now, the exact value of that volume or surface area is going to be f of x plus delta x when you plug in the exact value of that measured object. So the difference or error in your calculations of the volume or surface area or whatever value you were trying to get, that's going to be f of x plus delta x minus f of x. The exact volume or surface area or whatever you're calculating minus whatever you got when you use your measured value for the volume or surface area or whatever. That's where this delta y comes from. That's your propagated error. Now, something to note is that as delta x gets super small, meaning that your measurement is almost exact, it's very close to what the exact value is, delta y we are able to approximate with the differential of y, which we can then use to approximate our propagated error. Now, there are 3 types of error we're going to be working with in this class and on the AP test. There's propagated error, relative error, and percent error. So let's take a look at 3 different variables. Remember, your variable is just going to change depending on the type of problem. So no matter what your variable is, all of these 3 follow the same pattern. Your propagated error is just the differential of your variable. So here, if I wanted the propagated error of r or our radius, it would be dr. If I wanted the relative error, I would take that propagated error and divide it by the exact value of our radius. So dr over r is our relative error. If it's asking for the percent error, you just take your relative error and multiply it by 100. And each of these works the exact same way. The propagated error of a or our area is just dA or the differential of a. The relative error of our area is just dA over a, the propagated error over the exact value of our area. And then percent error is just taking that relative error and multiplying it by 100. Same thing for v or volume. The propagated error of v is going to be dv or the differential of v. The relative error is just going to be dv, the propagated error, divided by the exact value of the volume. So dv over v. And the percent error is just taking that relative error and multiplying it by 100.
People don't usually like me because they say I'm not down to earth. It's example time.
Now example 1 says use the information to evaluate and compare dy and delta y. So we are given a function y is equal to x squared in black right here, and we're given an x value c, which in this case is 1, so that's going to be at this point right here, and we're given a differential of x or dx equal to 0.01. And remember, dx is the same as delta x. These two things are equivalent. Now if we take a look at the graph, we have an x value c, which in this case is at x is equal to 1. We are then going to choose another x value, a certain distance away from x is equal to 1. And that distance we are going to call delta x or dx, and we know that's 0.01. We then have created a new x value over here, c plus delta x, or in this case, 1 plus 0.01 or 1.01. Now what we're trying to do here is compare dy and delta y. So dy, remember, is the differential of y. That's the difference between the y value of your tangent line at x is equal to 1.01 and the y value of your point of tangency down here, which in this case is 1. Delta y is the difference between the y value of your original function at 1.01, which is just f of 1.01, and the y value of your point of tangency. As delta x gets super small, as delta x approaches 0, these two y values get closer and closer and closer together, meaning that dy and delta y, the difference between the y value of the function and the y value of your point of tangency, and the y value of your tangent line and the y value of your point of tangency, become almost the same number. So let's find each of these values and see how close they actually are to one another. In order to find dy, what we're going to do is we're going to use that formula we had. Dy, the differential of y, is equal to f prime of x times dx. Now we're evaluating this at x is equal to 1. That's our point of tangency. So that's going to be our x value, or our c value in this case. So f prime of 1 is what we're going to try to find. And dx, we already know, is the differential of x. That's 0.01. Now f prime of 1 is just the derivative of our original function, the derivative of x squared at x is equal to 1. So what's the derivative of x squared? That's 2x to the first power. Then we plug in 1, we get 2 times 1, which is 2. We multiply that to 0.01, and we get that dy is equal to 0.02. Now let's find delta y so we can compare how close delta y and dy actually are. Remember, the formula to find delta y is f of x plus delta x minus f of x. And all we have to do here is just plug in our x value for x here and here, and our dx, or delta x, 0.01, here. So when we do that and simplify, we end up getting that delta y is equal to f of 1.01 minus f of 1. And this makes sense because delta y is the change in the y value of the original function at x is equal to 1.01 and the y value of the function at x is equal to 1. That's what delta y is equal to. So all we have to do now is evaluate this. F of 1.01 just means I take 1.01, plug it in the original function for x. Same thing over here. F of 1 just means I plug in 1 to the original function for x. If I square both of these and subtract, I end up getting delta y, or the change in y values here, is equal to 0.0201. And you see that delta y and dy are super close to one another. And that makes sense because as delta x, or dx, gets super small as that approaches 0, dy is an approximation for delta y. So these two should be very, very close because our dx, or delta x, is very small.
Close Encounters of the Third Kind, great film. You try.
Okay, doing the same thing here. This time we are not given a graph. We just have to kind of picture what's going on. We have a function, y is equal to 2 minus x to the fourth. We have an x value. That x value is our c value. It's 2 in this case. And we have our differential of x, dx, which is equal to 0.01. And remember, our differential of x is the same thing as delta x. Now let's mentally visualize what's going on here. We have our function, y is equal to 2 minus x to the fourth. That's our curve. And then we have a tangent line to that curve at x is equal to 2. Now, what's going to happen is we're going to have another x value a certain distance away from x is equal to 2, and that distance is 0.01. So at x is equal to 2.01, we're going to evaluate the function and the tangent line. And the difference between the y value of the function at x is equal to 2.01 and the y value of the function at x is equal to 2, that's delta y. The difference between the y value of the tangent line at x is equal to 2.01 and the y value of the tangent line, or the function, it's the same thing, at x equals 2, that difference is going to be dy. So let's calculate each of these and compare how close they actually are to one another. We're going to start by finding the differential of y. Remember, the formula for the differential of y is dy is equal to f prime of x times dx. Now, f prime of x, in this case our x, or our c value, is going to be 2, so we're going to plug in 2 here. Our differential of x, or delta x, they mean the same thing. That's going to be 0.01 in this case, so we're going to plug that in there. Now, f prime of 2, we're going to have to take the derivative of this function and plug in 2 for x. So how do we take the derivative of this function? We take the derivative of each term separately. The derivative of 2 is just 0. The derivative of negative x to the fourth, the negative stays out front, so you just take the derivative of x to the fourth with the power rule. That becomes 4x to the third power. So the derivative here becomes negative 4x to the third power. We evaluate that at x is equal to 2, and this is what we get. Now we simplify. Exponents first, so 2 cubed is going to be 8. Multiply that to the negative 4, you get negative 32. Then multiply that to the 0.01, and you end up getting that dy, or the differential of y, is equal to negative 0.32. Now let's go ahead and find delta y so we can compare it to dy and see how close they actually are to one another. So if you recall, the formula for delta y is just the change in the y values. And we know that in this particular question, our x value or c value that we're evaluating this at is x is equal to 2. So we're going to plug that in here. And our delta x is 0.01. So when we add these together, we get 2.01. And this makes sense, right? When we evaluate delta y or the change in y, it's the difference between the y value of our function at 2.01 and the y value of our function at x is equal to 2. So let's evaluate each of these things, then we'll just subtract them. So what is the y value of the function at x is equal to 2.01? Well, we plug in 2.01 to the original function and we simplify. Over here, doing the same thing, except we're evaluating f of 2. So we plug in 2 for x in the original function. 2 to the fourth is going to be 16. 2.01 to the fourth is going to be this decimal right here. We then subtract and simplify, and we end up getting delta y, or the change in y, is equal to negative 0.322408. And we look and see, yeah, delta y and dy, our differential of y, are very, very close to one another. And that makes sense because as our delta x or dx gets super small, dy will become a very close approximation for delta y. Now example 2 says find the differential dy of the given function. So we have our function here, y is equal to x squared, and we're trying to find dy. So this is actually super easy. All we have to do is take the derivative of this and then multiply both sides by dx, and we'll have dy all by itself on one side of the equation. So how do we take the derivative of this function? Well, over here, when we take the derivative of y with respect to x, that turns into dy dx. Over here, we use the power rule, and it just becomes 2x to the first power. Then we are solving for dy. So all we have to do is just multiply both sides by dx, and we end up getting dy, the differential of y, is equal to 2x dx. Part B, doing the same thing. So we're going to take the derivative of each side, then multiply both sides by dx. When I take the derivative of y with respect to x, it turns into dy dx. Over here, when I take the derivative of 2 sine of x, the 2 just stays out front by the constant multiple rule. So all I have to do is take the derivative of sine of x, which is just cosine of x, and then multiply the 2 back on. But I'm solving for dy. So I need to multiply both sides of the equation by dx, and I'm done. Part C, doing the same thing. So I need to take the derivative here. Remember, when you take the derivative of a radical, we have to rewrite this radical as a rational exponent. Then we can just take the derivative using the power rule. So when I take the derivative of y with respect to x, that turns into dy dx. Over here, when I take the derivative using the power rule, the 1/2 comes out front, and this becomes x to the 1/2 minus 1 power, or x to the negative 1/2 power. Now I don't want to leave my exponent as a negative 1/2, so I'm going to bring that back down to the denominator and convert it back to a radical. Now what I can do to solve for dy is just multiply both sides of the equation by dx, and I'm done. Part D, doing the same thing. I want to find dy, the differential of y. So I need to take the derivative of both sides. When I take the derivative of y with respect to x, that turns into dy dx. That's going to be equal to the derivative over here. Oh, that's going to require the chain rule because I have an outer function and an inner function. My outer function is going to be this something raised to the 1/2 power. My inner function is this something, x squared plus 1. So when I use the chain rule, I take the derivative of the outer function first, leaving the inner function alone. So it's going to be 1/2 x squared plus 1 to the 1/2 minus 1 power, or negative 1/2 power. And then I multiply by the derivative of my inner function. And the derivative of my inner function, I take the derivative of each of these separately. Derivative of x squared is going to be 2x to the first power. Derivative of 1 is just 0. That's how I get this 2x. Now, x squared plus 1 to the negative 1/2 power, I don't want to leave a negative exponent in my answer, so I'm going to take this x squared plus 1 to the negative 1/2, bring it down to the denominator with this 2, and make it a positive 1/2 exponent. Now what I can do is multiply this to the 2x. Remember, this is 2x over 1, so I just multiply the numerators together and denominators together, so I get 2x over 2 times x squared plus 1 to the 1/2 power. Now the 2's are just going to cancel each other out, and this 1/2 power I can rewrite as a radical again. And now it looks like I'm done, except, remember, I need to find dy. I'm finding the differential of y, so I need to get that by itself. So I multiply both sides of the equation by dx, and I'm done.
I could probably beat up Captain Kirk, but not Spock. You try.
Okay, doing the same thing here. I'm finding dy. So what I need to do is take the derivative of this function. Derivative of y with respect to x is dy dx. Derivative of ln of 2x. Oh, I have a function within a function, so this is going to require the chain rule. I'm going to take the derivative of the outer function first. Derivative of ln of something is just 1 over that something, so it's going to be 1 over 2x, times the derivative of my inner function, derivative of 2x, which is just going to be 2 times 1. So now what I do is just simplify. The 2 times 1 is going to be 2, and this 2 cancels out with this 2 in the denominator here, so I get dy dx is equal to 1 over x. Now remember, I'm finding dy. I'm just finding the differential of y. So to get that by itself over here, I just multiply both sides of the equation by dx, and I'm done. Here, doing the same thing. So I need to take the derivative of this function. Derivative of y with respect to x is dy dx. When I take the derivative of cosine of 3x, again, I have a function within a function. So it requires the chain rule. When I take the derivative here, I take the derivative of the outer function first, this cosine. So it's going to be negative sine of 3x. This stays the same. And then I multiply by the derivative of my inner function, the derivative of 3x, which is just 3 times 1. When I simplify this, I get dy dx is equal to negative 3 sine of 3x. Now again, I'm finding the differential of y, so I need to get that by itself. I multiply both sides of the equation by dx, and I'm done. Down here, doing the same thing. Need to take the derivative and solve for dy. So let's take the derivative of y with respect to x. That's going to be dy dx. When I take the derivative over here, I have a function times another function. So this is going to require the product rule. Remember, the product rule is the derivative of the first function times the second function plus the first function times the derivative of the second function. The derivative of x is just going to be 1. The derivative of e to the x, well, that's just going to be e to the x. Remember, derivative of e to the x is e to the x. Perfect. So now when I multiply 1 times e to the x, that's just e to the x. And then each term here has an e to the x that I can factor out, and I get that dy dx is equal to e to the x times the quantity 1 plus x. But I'm not done. I'm trying to find the differential of y, dy. So I multiply both sides of the equation by dx, and I'm done. Lastly, let's take the derivative of this function. The derivative of y with respect to x is dy dx. The derivative of 1 over x, remember, that's not going to be ln of x. What you do instead is you rewrite this as x to the negative first power. Then you use the power rule. So when I take the derivative here, this negative 1 is going to come out front. Then it's going to be x to the negative 1 minus 1 power, or the negative second power. Then I can bring this back down to the denominator, multiply both sides of the equation by dx to get dy by itself, and I'm done. Now example 3 says the measured radius of a ball bearing is 7/10 of an inch. The measurement is correct within 100th of an inch. Estimate the propagated error in the volume of the ball bearing. Then find the relative error and percent error. So the way I want you to solve these error problems is I want you to think about them like related rates problems. Just instead of rates, we're solving for error. What that means is that we can solve for the propagated error, relative error, and percent error by using the same steps we had with our related rates problems. So the first step in a related rates problem is to make a sketch. And we're going to label any constant measures with a number, and any numbers that are changing or have some type of error associated with them, we're going to label with a variable. And they already do that for us over here. Sweet. After that, we wanted our given quantities and our quantities to be determined. So what are we given here? We're given that the measured radius of the ball bearing is 7/10 of an inch. That means r is going to be equal to 0.7. That measurement, though, is correct within 100th of an inch. So that means that delta r, the change in r, has to be between positive 0.01 and negative 0.01. Next, we need to state, what are we trying to find? What are our quantities to be determined here? Well, we want to estimate the propagated error in measuring the volume. Now, remember, propagated error is just code for d whatever. So in this case, we're estimating the propagated error in the measurement of the volume. So that would be dv. That's what we're looking for. Now, why didn't I put anything about the relative error or percent error? Because if we find dv, we can find these two things as well. Relative error is just dv over v. Percent error is just dv over v times 100. So let's move on to step 2, which is to state our equation. What equation are we using here that we can take the derivative of and we'll have dv in it? Well, we need it to have a v in it then, right? So what is the volume that we're working with here? Well, the object we're working with is a ball bearing, which is a sphere. So let's use the volume of a sphere formula, which is 4/3 pi r cubed. We can then move on to step 3, which is to take the derivative of this equation. This is the only difference between our problem and related rates. In related rates, we took the derivative implicitly both sides with respect to time. Here, we're just taking the derivative normally with respect to our independent variable, which in this case is r. So we're just going to take the derivative of both sides with respect to r, and then we'll get dv by itself. So how do I take the derivative of this volume formula with respect to r? Well, the derivative of v with respect to r is just dv dr. The derivative over here with respect to r, remember 4/3 pi, those are both just constants. So I can leave those out front by the constant multiple rule and just take the derivative of r cubed using the power rule. So what's the derivative of r cubed? That's going to be 3r squared. I then multiply the 4/3 to that 3. The 3's cancel each other out. That's why I'm left with this 4 pi here. Now again, I just want dv. So I multiply both sides of the equation by dr, and now I have an equation that is solved for dv. How do I get dv? I now need to move on to step 4, which is to substitute my known quantities, my known values. So what did I write at the beginning were my given quantities? I know that r has to be equal to 7/10 of an inch. So I'm going to plug that in here. But what is dr? I don't have anything like that. Oh yeah, I do. I know that dr, or the differential of r, is equivalent to delta r. And delta r has to be within 1/100th of an inch, which means delta r is equal to plus or minus 1/100th of an inch. So for dr, I can plug in plus or minus 1/100th of an inch. I then plug this in my calculator and simplify, and I get that dV, or the propagated air in measuring the volume, is approximately equal to plus or minus 0.0615 cubic inches. If I were to round that to the nearest thousandth, I could say that the volume has a propagated air of about 0.062 cubic inches. Now we're not done. We also need to find the relative air and percent air. So let's start with the relative air. Relative air, in this case, is going to be dV over V. Now, instead of just using this rounded formula that I had here, I'm going to plug in what I know dV is equal to. It's 4 pi r squared dr. And I know that V is equal to 4/3 pi r cubed. So when I create an equation with dV over V, it looks something like this. Now, why don't I just plug in this stuff over here? Because, look, the pi's cancel each other out. This r squared cancels out with 2 of the r's in my denominator. And then I can simplify this 4 divided by 4/3 to 3 dr over r. Look at that. That's way easier to simplify. Now all I have to do is plug in my radius, which I know is 0.7. I can plug in my dr, which I know is delta r, which is plus or minus 0.01. And if I plug that in my calculator, I get that dV over V, my relative air, is plus or minus 0.0429. Now again, we are not done. We need to find the percent air. And this is probably the easiest one because you did all the hard work already. The percent air is just the relative air times 100. So dV over V times 100. So we just take whatever this is, multiply it by 100, tack on a percent to it, and we get that the relative air in measuring the volume here is 4.29%.
How'd the rocket lose its job? It was fired. You try.
Okay, this says a person is standing 35 feet away from the base of the Statue of Liberty and measures the angle of elevation to the top of her torch as 82.1 degrees. How accurately must the angle be measured for the percent error in estimating the height of the statue to be less than 5%? So again, because it's an error question, we're going to treat it exactly like we would if it were a related rates problem. We're going to use the exact same steps in order to solve this. So the first step in a related rates problem is to make a sketch, and we're going to label any constant measure with a number, and any numbers that are changing or have some type of error associated with them, we're going to label with a variable. So this person measuring the angle of elevation to the top of the torch of the Statue of Liberty is 35 feet away from the base. Now that measure is constant. That measure we know for sure. So that's going to be a number that we label. The angle of elevation, though, we're trying to figure out how accurately must the angle be measured for the percent error in estimating the height to be less than 5%. Meaning that the height and the angle of elevation we know are going to have some measure of error in it. Therefore, we're going to label each of those with a variable. I know it says the angle is 82.1 degrees, but again, that is what the person measured it to be. We are trying to figure out how accurate that measure must be for the percent error in estimating the height to be less than 5%. That's why it gets a variable. So now that we've made our sketch, we can move on to the next part of step 1, which is to state our given quantities and quantities to be determined. So what are we given? We're given that the person is standing 35 feet away from the base of the Statue of Liberty. We're given that the angle of elevation is measured to be 82.1 degrees. And we're given the percent error in estimating the height of the statue has to be less than 5%. Now remember, percent error is just relative error times 100. And relative error in estimating the height is DH over H. So that's why DH over H times 100 has to be less than 5%. Now, if I wanted to write this in terms of just the relative error, this is what the relative error needs to be between in order for the percent error in estimating the height with our given angle measure to be less than 5%. Now, we have stated all of our given quantities. What are we trying to determine? We're trying to figure out how accurately must the angle be measured. So how accurately must the angle be measured? Meaning what is the propagated error of our angle measure? Meaning what is d theta? That's what we are looking for. So now that we know what we're looking for, we can move on to the next step, step 2, which is to state our equation. What equation are we going to take the derivative of in order to get this d theta in our equation? Well, in order to get d theta, obviously theta needs to be involved. So what kind of equation can we set up with a right triangle using an angle like this? A trig ratio. So which trig ratio involves an angle, the opposite side, and the adjacent side? Well, that would be tangent. So we could say tan of theta is equal to h over 35. Now, I don't want to take the derivative of it like this. Instead, what I'm going to do is just solve this for h. So I could just multiply both sides by 35, and I get h is equal to 35 tan theta. Now, this looks like something I could take the derivative of. So let's go ahead and move to step 3, which is where we take the derivative of this with respect to our independent variable. In this case, that's this theta. So the derivative of h with respect to theta is going to be dh d theta. Over here, when I take the derivative of 35 tan of theta, the 35 just stays out front by the constant multiple rule, and I just take the derivative of tan theta, which is secant squared theta. Now, what I want to do is solve this for d theta. So the way I solve this for d theta is I first multiply both sides by d theta, then divide both sides by 35 secant squared theta. Now I have found d theta, so I can move on to my next step, which is to substitute all known values. Now we look up here and we see that theta is equal to 82.1 degrees, so we could plug that in here. But dh, we don't have anything for dh. We just know that dh over h has to be between negative 0.05 and 0.05. So since we don't have a value for dh that we can just plug in, we have to come up with another way that we can figure out what d theta has to be. So we're not going to use this. Instead, we got to use something else. Why don't we use this? So if we know that the relative error in estimating the height has to be between negative 0.05 and 0.05, we can then substitute in what we know dh and h have to be, right? We already solved for those over here. dh is equal to 35 secant squared theta d theta, and h has to equal 35 tan theta. Theta is going to be equal to 82.1 degrees, so we can plug that in here and here. And now the only variable left is d theta, which we could then solve for. Perfect. Again, it's a little bit different than what we normally do because we weren't able to just plug something in for dh. We had to go back and use this inequality that we created at the beginning. Now, let's solve this inequality for d theta. So we plug this denominator in our calculator right here, 35 tan of 82.1 degrees. Make sure that's in degree mode. We get that value, and then we multiply it to each of these numbers over here, negative 0.05 and positive 0.05. We then have to get d theta all by itself, so we're going to divide all three parts of this inequality by 35 secant squared of 82.1 degrees. When we do that, we get that d theta has to be between negative 0.006807 and positive 0.006807, which, if we wanted to write this another way, we could just say that the absolute value of d theta has to be less than 0.006807. Now, what does this mean? This means that the angle measure must be within approximately 0.0068 radians, so the percent error in estimating the height of the statue is less than 5%. Now, this is not a mistake. This is actually in radians. D theta ends up being in radians, despite this problem being in degrees. It's just one of the quirks of these error problems.